Use of symmetry in structures. In many instances, we can use reflective symmetry to facilitate the solution of a problem. Reflective symmetry means correspondence in size, shape, and position of loads, material properties, and boundary conditions that are on opposite sides of a dividing a line or plane. The use of symmetry allows us to consider a reduced problem instead of the actual problem. Thus, the order of the total stiffness matrix and total set stiffness equations can be reduced. Longhand solution is then reduced, and computer solution time for large scale problems is substantially decreased. Example: solve the plane truss problem shown in the figure. The truss is composed of 8 elements and 5 nodes as shown. A vertical load of 2p is applied at node 4. Node 1 and 5 are pin supports. Bar elements 1, 2, 7 and 8 have axial stiffnesses of under square root 2 AE, and bars 3 to 6 have axial stiffness of AE. Here again, A and E represent the cross-sectional area and modulus of elasticity of the bar. In this problem, we will use a plane of symmetry. The vertical plane perpendicular to the plane truss passing through nodes 2, 4 and 3 is the plane of reflective system, because identical geometry, material, loading and boundary conditions occur at the corresponding location on the opposite side of this plane. For the loads such as 2p occurring in the plane of the symmetry. Okay, so here we have the plane of symmetry. That means this side is identical to that side. Half of the total load must be applied to the reduced structure. Now you can see here we have 2p. If we get just one half, okay, so I will take just 1p, because this is 2p. 1p is for the left side and 1p is for the right side. For elements occurring in the plane of symmetry, here a half of cross-sectional area must be used in the reduced structure. So if we are talking about the elements here, we will take just a half of the cross-sectional area, okay, in the reduced structure. So we have here half of the cross-sectional areas of the elements in the plane of the symmetry, and we will take a half of the load. Furthermore, for nodes in the plane of the symmetry, the nodes, for example, 2, 4, 3, the displacement components normal to the plane of the symmetry must be 0 in the reduced structure. Here, if we are talking about the nodes in the plane of the symmetry like 2, 4, and 3, the displacement components here and here and here, normal to the plane of the symmetry, that means in this direction, in this direction, in this direction, must be set to 0. So I will put here the displacement normal to the plane, normal to the plane. Now you can see 2, 4, and 3. The displacement here 0. That is set u2 0. Now you can see here u2 0, u3 0, and u4 0. u2 0, u4 0, u3 0. Figure 22, this one, shows the reduced structure to be used to analyze the plane truss of the figure 21. Now we begin the solution of the problem by determining the angle theta of each bar element. For instance, element 1 here, this one, assuming x dash to be directed from node 1 to node 2. So the direction of x1 dash is start from 1 to 2, okay, or directed from node 1 to node 2. We obtain theta 1, this one, as a measured from the global x, this is the global x-axis, to the local x dash axis. So this theta is measured from the global x-axis to the local x1 dash. The table 3.2 is used to determine each element stiffness matrix based on the x dash axis shown in the figure for each element. There are a total 8 nodal components of the displacement for the truss before boundary constraints are imposed. Therefore, K, the stiffness, the global one, must be 8 by 8. That's mean here the total nodal components of displacement actually is equal to 8. Now, for element 1, now talking about the reduced system here, reduced structure, element number 1. This is element number 1. Now, if we're using this equation, okay, equation 23, I can calculate the stiffness matrix of the bar element number 1. Before that, for element in the table 3.2, for the element 1, 2, 3, 5, 1, 2, 3, 4, 5, I have the angle, and I have the cosine of the angle, and I have a sine of the angle, and I have the cosine square, sine square, and cosine multiplied sine. Why? We calculated all that items because I need it in this equation, I need it in this matrix. So for element number 1, actually I have got the stiffness matrix for element number 1. The same for element 2, the same for element 2, the same for element 4, for element 3, the same for element 4. Now you can see here for element 2 I have u1, v1, u3, v3, while for element 3 now this one directed from 1 to 3, so I have u1, v1, u3, u1, v1, u4, v4. Now, while for element 4 here, directed from 2 to 4, you can see directed from from 4 to 2. Now you can see u4, v4, u4, v4, and u2, v2. And eventually we are talking about equation or element number 5. Now, then we can calculate the total stiffness matrix, the global stiffness matrix, by adding all the stiffness matrices for all elements, and then we will put the boundary conditions that are u1 equal to 0, v1 equal to 0, and u2 equal to 0, u3 equal to 0, and u4 equal to 0, and we will put the load as well. So the finite element is, you can see here in the end, after reducing the finite element equation by using the boundary condition, I will get equation 83. This is minus b, this is minus b, not multiplied by p, this is minus b. Now I have 3 equations with the 3 unknowns. I can solve them simultaneously, and I will get v2, v3, and v4. Thank you.